Hello and welcome to another video on orbital mechanics. I'm going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, and I'm up to problem 2.10. And this problem is quite straightforward if you just plug the values into the equations. And what it's saying is just want you to find the eccentricity vector and the true anomaly theta of a spacecraft traveling above the Earth. It gives you R and V, and we already have a bunch of equations to do different things. The equation to get the eccentricity vector is R vector over R plus the eccentricity vector, which equals velocity cross angular momentum per unit mass over the gravitational constant mu. Now, if you rearrange this and put in our values, we have h because that is R cross V. It's quite straightforward, but I would like to have a look at why this is working a little bit. So I'm just going to draw an orbit. Not too bad. I'm going to put my focal points in. And I'm going to write down the equation for velocity, one of them anyway, and this is from the last video. So mu divided by h square root 1 plus 2e cos theta plus e squared. Right, now in this equation you'll notice we have this mu and this h, and you'll notice up here as well we have velocity here divided by mu and cross multiplied by h. So what this is basically doing, it's removing, in this particular equation, this is being added in because velocity has the magnitude that is related to the angular momentum and the gravitational constants, but E is not a magnitude concept, it's a ratio, and it's defined by square root of 1 minus b squared over a squared. So that doesn't include these magnitudes, so this equation here is actually removing them from the velocity. So let's go ahead and just remove those ourselves because we don't want those, right? So v squared equals 1 plus 2e cos theta plus e squared. Now we're going to do an example at this point here. This is RP, the periapsis, and at that theta is 0, so we're going to, that cos 0 is 1, so we remove that and we get that equal to 1 plus e from 1 plus e when you factorize that. Now that's squared, so you can lose one of those, right? So v equals 1 plus e. And if we take simple numbers, which I took before, and we'll say a equals 8 and b equals 4, so 8 here, 8 here, 4 here. E actually comes out to be root 3 over 2, or 0.866. And if you very simply look at this, you can see v equals 1.866. And if you do all the equations as normal, you will get v equal to 1.866 acting along this direction, right? Now, h is perpendicular. That is coming out of the page, perpendicular to both of these vectors because it's r cross v, right? So that's coming out of the page. And the original equation is velocity cross h, right? Which would be giving us, I think it gives us, in this direction, e, right? Now, it turns out that e is too big, so then it takes away the r unit r vector, so you get e bar equals r dot cross h over mu minus r bar over r. And so that ends up being, well, that's obviously magnitude 1. So yeah, E equals V minus 1. So in this situation here, well, in this situation, all of these end up being 1, you know, in some form or another. But if when you do cross with h, you get the E, which is, it's too big by 1, right? And so we subtract this, which is 1. And then we take another, so that all makes sense and it all works out fine. So we know it's true. If we take another point here, just to drive home the point, if we were here instead, right, and our velocity was going, say, this way, going the other way, our h would still be coming out of the page here, but then our velocity crossed with the h would be something like this, right? So that would be our E, well, our first attempt at it, which is not, it's not the final value. And so what it says is it's this is this value here, right? Subtracting r, unit vector r, right? Now this is our r here, and you may notice it's vertical. So by subtracting this vertical value, we're only leaving the horizontal value, right? It's probably this way, right? So that is our E. So by subtracting the r, it essentially shifts this value back into the horizontal, right? No matter where the r is, it's effectively removing that outside vector and bringing the angle back into the center of the, down the middle, right? And you know, I can't sort of work out the maths completely, but you know, when you actually do it out simply, or for an example, you can see that this is how you get the eccentricity vector, and it does, this here equation does make sense when you think about these values and these directions and the two examples here and here, and using simplified mathematics, you can get to the values. So when you actually use that equation to get, yeah, just rearrange it, you'll get the answer on the screen in the book. And then if you want to get the true anomaly, you just have to rearrange one of the equations to get the angle. And the one that I did, yeah, I just did. So theta equals cos inverse h squared over u r minus 1 divided by E. Yeah, pretty sure that's right. Yeah, I started with r equals h squared over mu 1 over 1 plus E cos theta. So that is mu r over h squared equals 1 over 1 plus E cos theta. And so that's h squared over mu r equals 1 plus E cos theta. And then that's minus 1 over E. Yeah, so that's correct. Using this equation here, you get theta, and that's 2.10. Sorry, it's a bit messy, but yeah, I'm just trying to get my head around this equation myself, and I stumbled upon these two examples and this simplification for this example to give us the eccentricity. And I'll have a MATLAB script that does this as well. Thank you, goodbye.